Thank you, Yuri, and thank you for everyone attending. What I'm trying to cover, as indicated by the title, is to go from prediction and forecasting through to issues around climate change. Most of the talk will be on the thorny issue of climate change, and given that most of all of the session that follows on forecasting, I'm not going to try and go over the same ground. So the topics I'm going to cover are aspects of urban water planning that are relevant to climate science. Then look at issues relating to definitions of technical terms, particularly predictions, forecasts, projections and scenarios. And why I'm doing this is I've been involved in this sort of work now for 16 years, and I've continually see these terms used interchangeably, not only by climate scientists and water planners, and I think that leads to a great deal of confusion as to what a climate change scenario actually is. I'll then touch briefly on the issue of stationarity, which is quite important in terms of trying to determine whether climate change is potentially a threat now or an emerging threat now. Look at the issues around sources and propagation of uncertainty. Look at some of the underpinning assumptions made in climate change assessments which most people don't seem to dwell on or conveniently ignore. And given the amount of uncertainty involved in climate change assessments, look at some of the broad approaches to systems planning and how they might be used. I'll then highlight a new tool that's been developed by CSIRO, which is meant to facilitate the use of climate change projections from the latest IPCC report in practical contexts. I'll then talk about robust adaptation strategies and finish up on what I regard as prudent action under climate uncertainty. So the comments I'm making here about urban water planning were captured by an Australian consultant, and the scope of the study was limited to urban water planning in Australia. And what they found was there was a set of characteristics that were common to all of the different water agencies in Australia. First of all, the extent to which past changes in streamflow or groundwater recharge were recognised, and that means that some agencies only looked at part of the record, not all of the records that are available for their planning. Degree of reliance on the historical record, whether these people even used paleo information, for example, or looked at climate change projections. Level of service requirements, which tend to vary from agency to agency, and here we're talking about reliability and resilience standards. Degree of reliance on reductions in water demand. In a lot of urban water agencies in Australia, a lot of this has already been hardwired in terms of user pays, in terms of water charging, but also in economic incentives to have water efficient appliances installed in homes. A willingness to consider non-traditional sources. As a result of the Millennium Drought, which will be talked about tomorrow in Australia, there are a lot of now desalination water plants in the major capitals in Australia, but there are a few that are now even thinking of water recycling as a means of water, because there's only so many desalination plants you can build. They're very, very expensive and very energy hungry. The extent to which climate change projections are considered, and the extent to which contingency plans and triggers are identified and articulated, and I'll demonstrate what I mean by that later. So when we come to definitions, I've lifted a schematic here from a paper that was published 9 years ago now, and in the vertical axis we've got uncertainties and predictables, and an arbitrary timescale. And when you look at small values of time, as you might expect, when we're thinking about predictions or forecasts, our quantities or the accuracy of our predictions are quite high, and the uncertainty is low. But as we move to 1, 2, 3 or 4 units ahead in time, what we see is the predictability starts to drop off quite rapidly and the uncertainty start to rise. So when we're talking about prediction, it's really about a specific statement about the future. For example, tomorrow there will be 25 millimetres of rainfall. Forecasts, if you think of numerical weather prediction, they might try to describe maximum minimum temperatures and the likelihood of rain 5 to 7 days out. Projections is commonly what you see come out of the IPCC, where they have now what they call representative concentration pathways, which are forcings which tell us what could possibly happen if certain assumed conditions prevail in the future. And lastly, there's these things called scenarios, which is a series of events that could lead us from the present to a plausible but not assured future situation. Quite often these last two terms are also used interchangeably, but to me they're two different things. There's no reason why a scenario has to be a climate change projection in the IPCC sense. Many of you would be aware of this already, that here are some sources of uncertainty, whether we're looking at the historical record or climate change projections. I don't think anyone would argue, either in climate science or the hydrological sciences, that we have all the facts we need to do the work required for water planning. When we start looking at our data, it tends to be very noisy. And we also have a lot of observational data where the measurements are made at spatial and temporal scales that aren't appropriate for the problems we're trying to solve. We then come down to structural uncertainty, and this is true whether we're talking about hydrological models or climate models. Different models have different model configurations, they have different internal physics. And parameter uncertainty, and even in global climate models, when you're talking about trying to characterise processes that occur below the or a finer spatial scale than the grid actually used inside, the computational grid used inside the GCM, they do have estimatable or tunable parameters in these schemes, and because of that there's actually uncertainty being introduced there. And then finally we come to initial and boundary conditions, and for climate change projections the representative concentration pathways are boundary conditions. When we come to the issue of stationarity, there are a lot of papers in both the climate and hydrological sciences where people are declaring that there are trends and so on. But I don't think a lot of people will really appreciate that what you see is highly dependent on the origin of the time series that you're dealing with and the period of record. And this example here is taken from a paper Dan Slettenmeyer and Steve Burgess published in 1978, showing the annual tree ring growth index for a limb of pine that's in a particular location in Montana. And this had a much longer record than 140 years, but this sub-record here was used to demonstrate a point. And if you look at the whole time series, yes, there are excursions up and down, but it doesn't look particularly unstationary. But if you look at this grey box here over that period of about 60 years, you can see there's a marked trend. And that's only because, again, of the origin and the period of the record that we were looking at. If we want to look at something a bit more closer to water planning, where I live in southwest Western Australia, we've been actually going through a multi-decadal drought since about the mid-70s. It's had a massive impact on water planning in our state, and at the moment we've spent about $2 billion in seawater desalination, which will probably carry us through to about 2025, and then the next set of investment will have to occur. This has been largely due to a rainfall decline. Our rainfall in that part of the world is very Mediterranean patterns, winter-dominated rainfall, and most of the decline has actually occurred in the 3 months, May, June and July. And this animation here is just based on observations at about 64 daily rainfall stations that had fairly good records over this period from 1940 to 2010. Prior to 1940 there are very few stations. What you're seeing here is actually a statistical model fitted to the data. It's called a generalised additive mixed model, which takes into account spatial and temporal correlations in the data. And before I hit the button, what you'll see is in this particular part of the world, these are rainfall totals for these seasons. And here is the wettest part of the southwest corner of Western Australia, and up in here in the eastern wheat belt is the driest. And what you'll see from about 1940 to 1958 is actually these contours move inland, the region got wetter, and then somewhere around 1958 they actually start retreating back to the coast. And then from about 2000 there's a quick step quite dramatic one at that. So let's see if I can get this to work. Okay, when people have been looking at those sort of records, and you see it right throughout the hydrological and climate science literature, people have become very interested in trends, and one of the most popular tools for assessing trend is nonparametric statistics. What's evident when you see a lot of these studies and you try to read deeply what's there is because these techniques are distribution free, many people appear to be assuming that they're also assumption free, which is not true. If you do delve a bit deeper into the literature with all of these techniques, there are two underpinning assumptions here. One is that the data are independent, so there's no order correlation in the data at all. And the second one is that they're identically distributed throughout the series. The two most popular techniques you see used in the literature are the Mann-Kendall test, where people use this for trend, but there's also an underpinning assumption in that you're dealing with a monotonic trend. And as we saw with that Western Australian rainfall example, the trend is not monotonic. It's certainly non-linear. And then there's the Pettit test, which is supposedly a change point detection test, but you can only find one line in that whole paper that even remotely refers back to that underpinning assumption. What happens is if the data you're using or the trend is there but is non-monotonic, you start getting what are regarded as false positives. So you start getting results that appear to be statistically significant, but they're certainly not physically significant. The other thing too is that as a journal editor, you get very tired of seeing papers where people assume this 0.05 level, there's something special about that, and anything where you have a probability below that is statistically and therefore physically significant, and anything above it is not. And I always remember as an undergrad student when I struck this, when you're dealing with a sample size of 30 and you've got a result of 0.051, you're trying to tell me that another one or two data points mightn't change that conclusion. Another one too is when people start using batteries of these sort of tests, because they're very easy to implement. There's a lot of software out there, but many people don't appreciate that you are in fact doing multiple testing, and that the error, just by chance, the errors that you will incur will grow with the number of comparisons. The other thing too is in terms of statistical science, so we're talking about people working at the cutting edge of statistics, they don't use these sort of techniques anymore. They've moved on and used computer-based methods with model-based statistics, and I'll show you an example of that in a moment. I mentioned this rainfall in southwest Western Australia, the decline. This is the inflow into the 11 supply dams in the system that supplies Perth. 1975 is about here. So you can see there is a bit of a drop here, a period of growth after that, and then a marked decline. And because people have been using things like the Pettit test and so on, they'll end up with a probability value of about 10 to the minus 7, so this is highly statistically significant. The only problem is when you look at a data set like that, for example, it's quite obvious that the data are not necessarily independent, but certainly they're not identically distributed, because you just look at the change in the mean and the variance. An old approach to dealing with this sort of problem is to take a square root or a log transformation, which has been done here, and a local linear regression has been fitted through that series. And the software that my collaborator and I were using from the University of Glasgow actually has a hypothesis testing framework associated with it. This thing has a smoothing parameter, which there are means of getting reasonable values for that parameter. And here we're looking at testing the null hypothesis of no trend. And you can see a dashed line there that's well below the 0.05. It's about 0.04 over very wide ranges, that smoothing parameter. So what it's telling you is, yes, there is a very marked trend there and it's non-linear. There's also a test for a discontinuity, and this is meant to be a change in mean level test. And what you see here is the probability values over that range, a smoothing parameter, are above 0.1. So what it's telling you is the evidence for a breakpoint isn't that strong. And that is heavily contrasted to what you get for something like a pellet test. What does this matter? Well, what water planners have been doing is assuming as time has gone by that the mean level has been dropping and making their plans on that basis, but quite clearly what's been happening is that the flow has been decreasing rapidly with time rather than going down in steps. So the issue here is more immediate than what's being given credit for. When we come to climate change assessments, this is based on the fourth assessment report, but it still holds true in terms of the steps that have gone through for a climate change projection. You start with some socio-economic assumptions. This now has been replaced by the representative concentration pathways, but they are used to drive a general circulation model. Then there'll be some sort of regional model used for downscaling, be it dynamic or statistical or both. And then we come down to an impact simulation. The problem with all of this is a lot of these models here are highly nonlinear, and any small perturbation in the data here will lead to a marked response in the output once you come down to here. It gets even a bit more insidious. This again is harking back to the previous IPC assessment report, comparing the models that we use as the basis for that report. And what we've done here is to compare how well these models do at large-scale phenomena like the El Nino subtle oscillation, how well they represent the probability distributions of rainfall and temperature across the continent, and how well they do that job when you start looking at something the scale of the Murray-Darling Basin, which is a very large river basin in Australia. And what you can quickly see is that models that handle large-scale phenomena that well don't seem to handle the regional scale, and vice versa. So it's very hard from my perspective, to pick models that are fit for purpose. You would hope that you'd find models that do well at the large scale as well as the regional scale. When we come to China's climate change impact assessments, very rarely do you see mention of changes in the water efficiency of plants. We know most plants will respond well to increasing CO2, provided there's sufficient water and the temperature increase is not too high, and that will impact on the water balance. In places where we call them bushfires, Americans call them wildfires, take place, there's an issue there, not only in terms of water quality. Once the forest burns down, water puts the ash into the streams, but also as the forest starts to regrow, it starts to use a lot more water over a number of years. There's also the issue as the rainfall and temperature change, so will the vegetation composition and structure, and again that'll have an impact. Another one that doesn't seem to be widely appreciated is that with the global climate models, a lot of the code in these models is actually shared. So even though you might feel confident you're using 8 GCMs, the number of independent GCMs you're using is probably far less than that. There's the issue in terms of hydrological models where the parameters are sensitive to climate forcing. There's now a plethora of statistical downscaling models, but in fact the number of downscaling models just continues to grow, which just increases uncertainty. There's also, in terms of flood risk, this issue of how antecedent conditions might change, and when you look at most impacts or studies of impacts of climate change on surface water, usually the results are reported in terms of changes in the mean. Rarely do you see anything about changes in antecedent conditions. And also rarely do you see anything said about changes in the flow regime, and I'll point out why that's important in a moment. Another one that cropped up during the Millennium Drought, and Francis Chew and I were at the same meeting, was there was a Victorian water planner who made the statement that in the middle of the drought in Western Victoria, which is a state in the southern mainland of Australia, it was worse than the worst case scenario for 2070. And her response was, can you explain this? Why would this be so? And I think to me this highlights why we need scenarios as well as projections. In terms of looking at this change in regime rather than just changes in means, this is a study I was involved in. It was published many years ago now, looking at the Murrumbidgee River at Maud Weir. This is a very large river in Australia, part of the Murray-Darling Basin. I won't go through the details of the climate change projection and the model that we used at all, but if we look at the flow duration curve, the blue curve there is for the current climate, red for the future climate, and what you notice for low flows there's not much change at all, but certainly for high flows there's a dramatic drop, and there was in fact a 52% reduction in flow occurs, but 45% of that 52% is all on the higher end. And if you're interested in things like flood risk, that's important. You find with these large rivers in Australia, they've got very wide flat plains, and there's a lot of fauna and flora there that rely on periodic flooding of those floodplains. And when you see something like that, you know the ecology of those floodplains is likely to change. When we're dealing with issues of uncertainty, this is a paper I came across in the ecological literature actually, and it's looking at comparing uncertainty with the degree of control. And when I was an undergraduate student many years ago, in the water resources literature there was a lot of focus on hydropower dams and coming up with operating rules using linear programming or stochastic dynamic programming, trying to look for optima. And that's quite appropriate where you have a higher degree of control and a low level of uncertainty. In practice though, what I observed, certainly in Australia, is most people used hedging, so they basically tried to eliminate or minimise risk. And there's an unwritten law of politics in Australia that no major city in Australia will run out of water, and that is why that approach was taken. But as Australia has grown and water demand has grown, there's now more of an emphasis on adaptive management, and the speakers to follow will certainly be able to amplify that message. But when we start looking, and here, this is where the issues of prediction and forecasting are very useful. And once we start going out the order of decades or multiple decades into the future, we're really getting into scenario planning territory. In terms of what CSIRO has tried to do in presenting information to facilitate climate change impact assessments, this is just a simple example of the tool that's been developed. This is all with the latest global climate change models. And it's showing a table for the southeast corner of the country, looking out to 2060 under a medium represented concentration pathway of 4.5 watts per square metre in 100, and it's tabulating GCM simulated winter rainfall, percent change in temperature in terms of degrees warming. This is relative to the 1986 to 2005 period, and they've got some categories here they've devised, and they found that there were 34 global climate models that did a reasonable job for that part of the country. And by going through this sort of process, you can actually see where most of the models lie in terms of potential changes in rainfall and temperature. So for example, if you wanted to keep the number of projections or scenarios down to a reasonable level, you could concentrate on the models that fit within these two boxes here. But if you wanted something a bit more, to include something a bit more severe, you might actually pick one of the models out of these two boxes as well. So you're looking at about 3 or 4 projections to actually make your assessment. Having done all of this, I don't know whether there are any professional water planners in the room, but I remember when I first got into this area, I quickly got the message that climate change is just an additional risk. There are others, and our last speaker actually brought some of those up. And there was an approach, particularly with the fourth assessment report, where people would get into cranking models and putting projections through
and then trying to come up with some sort of best guess or what I would to recommend to water planners. But I think to a lot of people who are professionals in the planning area, there is a better approach, and this is to look for what are called robust solutions. So one possibility is to look for solutions that give us a benefit now, even in the absence of climate change, will put us in a better place in the decades ahead. Another possibility is to use a reversible solution. So this thing has a short life, and when you start reaching the end of that life, you can actually make an assessment because you've got a cheap to retrofit design. Another one is having a safety margin, the old traditional engineering approach, particularly if you can over-design at a small cost, and particularly if you have a good look at what you're actually doing and try to make sure that if the structure does fail, it's fairly safe if it does fail in terms of the downstream impacts that would occur. Many parts of the world already have soft, robust solutions in that they have updatable water plans that come out about every 10 years or so. By going through this sort of approach, you aren't really hung up on trying to predict what the climate and weather is going to be like multiple decades ahead. And I think the key thing, though, like all of these sort of policies, is you do need to be able to justify these things economically, but they also have to be acceptable to society. Now, I just tried to, in the time available, give an illustration of one of these no regrets situations. This is again looking at the moored weir pool. I'll only look at the graph here on the right hand side. One of the problems that used to occur here was blue algae, which is highly toxic to livestock and can't be used for irrigation on farmland. And as a result of some work that was done only for about a year or so in the moored weir pool, it was quickly found that the algal blooms needed water stratification to occur, and the bloom would occur 14 days, and it was amazing, the evidence was very strong that it was 14 days after the stratification had took place, but also that once that stratification was broken, the algal bloom would disappear. So if we look at the bloom days per year, and this is looking for the current climate, and this with no adaptation, so we're not changing how we operate this weir pool. As you might expect, once you get into scenarios that are hotter and drier, and that's true for this part of the world, things tend to get worse if you don't adapt. But then there are these other two curves here on the left-hand side with the labelled targeted pulses. And what this is that we came up with the idea of, okay, if you need 14 days of stratification for the algal bloom to occur, once you do get stratification, you start banking a little bit of water, like 10% each day for 10 days, and you send a pulse down through the weir pool. And as you can see, it's highly effective in decreasing the number of bloom days per year for both current and projected climate change conditions. So this is what I mean about a no regrets policy. This is my final slide. One of the problems you always have when you write these sort of slides is trying to keep the words short, but things end up being ambiguous. If I'm talking about multiple decades ahead in terms of climate change, to me, I think there's been too much of a focus on prediction. People have been treating projections as projections as predictions. They're not. They're just something like a plausible future. And as emphasised by Dr. David Rogers this morning, preparedness in that context is certainly highly important, but I think it's also highly important in the present day that we focus not just on better predictions, but also on preparedness. I think when we're going through these sort of assessments with an aim to changing policy, we do need to reflect on reliability, resilience, and showing evidence that there are immediate benefits for adapting now rather than later. I think a key to this is just choosing a small number of projections and scenarios,
One such scenario, for example, and this is coming out in the Murray-Darling Basin Plan, and Francis will be talking about that, where they do consider projections. They actually have another scenario there related to what they saw in the Millennium Drought and that this thing might come back soon. And I think that's a style of planning we've got to get used to, rather than relying just on the historical record or just on the historical record and climate change projections. We've also got to help some water planners get away from the idea of choosing the most likely or the best guess. I've been confronted by requests like this very often in the climate change area, and we should be focusing on the low probability, high impact events, and we heard a lot about those earlier this morning. Another thing too, in terms of the costs of immediate adaptation, you also have to consider if the projections or scenarios are reasonably right into the future, there's going to be some cost of retrofitting out there, and an assessment needs to be made about what those costs are, and are we better to adapt now or postpone and adapt later. All of this means that we need a continuous cycle of planning and evaluation, and I won't go through all of these points, there's not time. I think we need not only adaptive prediction but also adaptive government arrangements. People have to get used to the idea that just because I had this amount of water last year doesn't mean that's what I'm going to get this year. And also in terms of markets and pricing, there's still a reluctance to price water according to availability in Australia, which I think is a mistake. I think the last point I'll make in terms of socio-political acceptability, I've seen it time and time again where people will leave contact with the public well after they've done all their impact assessments and so on, and just put it on the table as a fait accompli. And in my experience, that's just a recipe for disaster, and you will not see your new dam built or whatever. You have to engage with people early, and you have to take them along a journey as to why these new dams and so on have to be built. So